is always a solution of the system. Now we are interested in finding a non-zero solution of this system. So that means we are interested in finding the value of lambda so that this system will have a non-zero solution. And from there we see that this will happen only if the determinant of a minus lambda I is equal to 0. And from there we get a polynomial in lambda. This is known as characteristic equation. So that means if we solve this polynomial for lambda, then we can find the values of lambda for which the system of equation will have a non-zero solution. Okay, so let us consider one example to see how this works. So consider a very simple example. A is a 2 by 2 matrix. Now A minus lambda I2 is the identity matrix of order 2. This will be equal to, you substitute the value of A 1 2 3 2 and substitute the value of lambda, substitute the value of the identity matrix 1 0 0 1. You subtract this, you get this one 1 minus lambda 2 3 and 2 minus lambda. The characteristic polynomial or characteristic equation of A is determinant of A minus lambda I2 is equal to 0. So first of all, we find this one is A minus lambda I2. Okay. So we find the determinant of this. Determinant of this will be lambda square minus 3 lambda plus minus 4. So determinant of this matrix is lambda square minus 3 lambda minus 4. From this equation, the characteristic equation, this should be equal to 0. Okay. Now this is a polynomial of order 2, so it will have 2 roots, and one can easily find these 2 roots as lambda is equal to 4 and minus 1. Okay, so this means the eigenvalues of A are 4 and minus 1 in this example. Now corresponding to 4, we have to find a solution which is non-zero. So we substitute the value of lambda in this equation. So if you put lambda is equal to 4, you have A minus 4 I is equal to 0. This is the case when lambda is equal to 4 and x as well. So from here you can say that Ax is equal to 4x. Now this is a system of homogeneous equation. You know how to solve the system of homogeneous equation. We have seen in the previous lecture. So you solve the system of homogeneous equation to get the value of x. When you do this, this value will come out to be, x is equal to 2 3. Okay, so corresponding to the eigenvalue 4, the eigenvector is 2 3. So that means if I take lambda is equal to 4 in this system, we will be able to find a solution which is not 0, and the solution is 2 3. Similarly, the second eigenvalue is minus 1. So if I substitute minus 1 in this equation, then I'll get I will get this equation. And this is again a system of homogeneous equation. And you know how to find the solution of the system homogeneous equation from previous lecture. So this solution will come out to be 1 minus 1, the vector 1 minus 1. So this means corresponding to the eigenvalue lambda is equal to -1, we are able to find a non-trivial solution which is 1 minus 1. Fine. Is this clear? Any question here?
No, sir.
Okay, so now we can see this geometrically as well. Let us consider this example itself. So you have this matrix 1, 2, 3, 2, and consider the case lambda is equal to 4. When lambda is 4.
So,
yes.
So when we are using this to find non-zero solution, so every time when we are finding non-zero solution, we will get infinitely many solutions.
Yes. I'm coming to that. Yes. So infinitely many solutions, because whenever you have a solution, you can multiply this by any real number other than 0, you get another solution.
And
okay.
so said that the above system has non-zero solution if and only if a minus lambda I is equals to 0.
Yes.
So how you can say that? Like when we read this in 11th and 12th, we got we know that when the determination of any matrix is 0, then we can have either infinitely many or we cannot have just no solution. So how can we say that it is always
So you have a system of homogeneous equations. So you see that this is a system of homogeneous equation.
Yes, sir. Okay.
So if you have a system of homogeneous equation, if you say that left hand side is b, so you have bx is equal to 0, and b is invertible. That means b inverse exists if determinant of b is non-zero. So you can multiply both the sides by b inverse, pre-multiply. So you have b inverse here, you have b inverse here. Right hand side is 0. Left hand side you get I into x. I into x is equal to 0. That means x is equal to 0. Right. So you get a unique solution. Is this fine?
Yes, sir.
Any more question? Okay, so no more question, then we go back to our topic. So I was discussing the geometric interpretation of this eigenvalue and eigenvectors. So if I take lambda is equal to 4, then we have seen that the solution, the eigenvector is 2, 3. So you can multiply, because this is a, on the left hand side you have ax. So we write 2, 3. Let's do the multiplication and give me the values. Just now.
Eight, 12.
8 and 12.
8 and 12. And what is, so this is the left hand side, ax is equal ax. And right hand side is lambda x. Lambda in our case is 4. And this is 2, 3. So this is 8, 12. So these two are equal. So what do we get from here? Now let us look at the eigenvector in the xy plane. You have x here, x-axis, y-axis here. Eigenvector is 2, 3. So on the x-axis, this is, let's say, 1, 2, this is 0. And y-axis, you have 1, 2, 3. So this is here. This point is here. So this is my vector. 2, 3. Now when you multiply, when you write ax, the outcome is h12. H12 will lie where? You can write 3, 4, 5, 6. So yeah, on this line, obviously, 8. And so basically it will lie on the same line. Let me put in a different color. But the length of this will increase. This is, let's say, h12. Right. So earlier the length of the vector was this. This was the original vector. And now if I multiply this matrix 1, 2, 3, 2 to this vector, its length will increase. If you have another matrix, so in this example, the length is increasing. You may have another matrix where the length is decreased. So basically we are then looking for a constant 4 so that you can get the same length vector on the right hand side. So this lambda x is equal to you get 8 and 12, the same vector. Okay. So basically when you have
lambda equals to 1.
Lambda is equal to 4.
So we need the same vector, no? So
yeah, so for same vector, because this is your eigenvalue 2, 3. So if lambda is 4, then you are increasing the length by 4 times of this vector. Okay. So this is the real purpose of finding the eigenvalues and eigenvectors. And in real life, this has a lot of application, particularly in statistics, where people are interested in summarizing the data, or you have a large number of data set and you are interested in identifying the components of the data. For, let us say, data are related and there are 4 components. So there that or 4 or some factors. So the principal component analysis in statistics, this is used. Factor analysis, this is used. In machine learning also, you will see later, if you go on for higher studies in this area, or if you work in this area in industry, you will see that this is widely used. So the applications we are not to discuss in detail, but this has a lot of applications. Okay. So now let us go to the property. Any questions so far?
No, sir.
Sir, can you please repeat that geometry part once?
Yeah. Okay. So it's still there. I thought it is deleted. So when you have you have a vector x, you multiply this vector by a matrix. So this is n cross n, and x is your n cross 1. So outcome will be some vector y n cross 1, right? So basically this is the, so you have, let us say you have original vector x, and you multiply this by a matrix A. So basically this the impact of this matrix is that you get another vector, right? So this you can treat as some kind of force. You have let's say some position of the particle, and the force is acting like a matrix, so that these particles move from its position to some other position to get a new vector. Okay, so this is the definition of AX, right? So in this, if you have the eigenvector and the eigenvalues, then what we are doing is that when we translate, or when we reposition this particle, so original position was at the point 2, 3, and then you hit this by a matrix. So the position goes to 8, 12. Okay. So this position you can determine, instead of the matrix, this position you can determine by a single number, lambda. You hit a single number, say hit a real number 4, and you go to this position. Right. So in a way you see that the matrix has 4 data, 1, 2, 3, 3, 2. So instead of dealing with these 4 data, you are only dealing with a real number. So now you can imagine this on a large scale. You have a big matrix. This big matrix is now replaced by a real number. The work that is done by a big matrix is now done by a single real number. Okay, so in that way, this is useful in application. Instead of using the big matrix, you just use a single number to identify or to summarize the data.
Got it.
So this is used in principal component analysis, factor analysis. These places, this concept is very much useful. And how they are used, you will learn if you take some advanced course on statistics. Okay, so this is the application is not part of this course, so I'm not going to discuss that application. Right, but you remember that this has wide applications, and I have given you some hint of how this can be applied. You have a big matrix. The big matrix is making some impact on the vector, which you are identifying with the help of just a single real number, the same impact, which is lambda, the eigenvalue. Okay, so now property. If X is an eigenvector of A corresponding to the eigenvalues of lambda, then Kx is also an eigenvector of A corresponding to lambda. And this was, there was one comment just a couple of minutes ago, that if we are able to find one eigenvector, we will be able to find many eigenvectors. Eigenvectors are not unique. Corresponding to eigenvalue, we can find many eigenvectors. Okay, so this says that X is the eigenvector corresponding to the eigenvalue lambda. So this means that AX is equal to lambda X. And now we want to show that Kx, where K is a non-zero real number, is also an eigenvector corresponding to lambda. So we can easily show this. So we start with A into Kx. K is not 0, so we can write this as K into Ax. And Ax, since X is the eigenvector corresponding to lambda, This is given to us. So AX is equal to lambda X. So we use this relationship here. So we can write this as K into lambda X. And then you can write this as K into lambda in bracket and X. So this means that this means that Kx is also an eigenvector of, and I have rearranged it wrongly, so you should write it as this is equal to K lambda X, and now you can write this as lambda into Kx. Okay, so you have Kx here, Kx here, the same vector. Okay, so we can say that Kx is an eigenvalue corresponding to lambda as well. All right. We have one example here. Find the eigenvalues and eigenvectors of a matrix A. So here you can easily see first of all you have to find the characteristic equation. So what is characteristic equation? Characteristic equation is A minus lambda I. Determinant of this is equal to 0. So you substitute this value, substitute the value of A. You can do this calculation now. Do it now. Substitute this value of A here, and then give me the characteristic equation. So do it now.
So it will be lambda cube minus 6 lambda square plus 11 lambda minus
Lambda cube minus
6 lambda square
6 lambda square
plus 11 lambda
11 lambda
minus 6
minus
6
6.
is
This is equal to 0. So this is the characteristic equation. Now this is a polynomial. This is the characteristic polynomial is a polynomial order 3. So this equation will have 3 roots.
2, 3, 1.
So can you find the roots? So the
Sir,
roots
2,
1,
3,
2,
1.
3. 1, 2, 1, 2, 3.
Lambda is equal, 1 is equal to 1, lambda 2 is equal to 2, and lambda 3 is equal to 3. Okay, so these are the eigenvalues. The solution of the characteristic equation are eigenvalues. Now you start one by one. You take lambda is equal to 1 and then identify then find the eigenvector. So take lambda is equal to 1. So if you take lambda is equal to 1 in the relationship Ax is equal to lambda x, if I take lambda is equal to 1, we have Ax is equal to x, right? That means A minus I is equal to x. Now this is a system of homogeneous equations. Substitute the value of A in this equation and find the value of x. Non-trivial solution, not 0. Solution is not 0. Now you can do it now.
1 minus 1, 1.
Yeah, so the solution comes out to be x is equal to 1 minus 1 and 1. So corresponding to the eigenvalue lambda is equal to 1, the eigenvector is 1 minus 1, 1. Now you can repeat the same thing by taking lambda is equal to 2. So you take now lambda is equal to 2. And then calculate the eigenvector. So what do you get? And similarly for lambda is equal to 3. So when you do this lambda is equal to 2, you get the eigenvector as 1, 0, 0. And if you take lambda is equal to 3, the eigenvector will be 1, 1, 1. Is this okay?
Sir, corresponding to 2, I am not getting 1, 0, 0.
क्या आ रहा है?
0, 0, 0 ही आ रहा है, मतलब ट्रिवियल आ रहा है.
नहीं, ट्रिवियल तो नहीं आएगा क्योंकि ये तो आइगन वेक्टर आइगन वैल्यू है, तो ट्रिवियल तो पॉसिबल ही नहीं है.
x1 तो ऑल रियल हो सकता है और x2 x3 0 होगा.
Yes, sir. Yes,
अच्छा.
sir. X1 can be real. X2 and X3 are 0.
X2 and
Yes, sir.
X3
Yes, sir.
basically
Yes.
X1 is a free variable, so you can assign any real number.
Yes,
So
sir.
if you assign 1, then you get 1, 0, 0. Fine.
Yes, sir.
And
We can
similarly,
assign the x1.
you can assign any real number because we have already seen that if x is the eigenvector.
Rank is 2, therefore one free variable.
And in also when x1 equals to given 1 minus 1 1, we can also write this as minus 1 1 and minus 1.
Yeah, because there will be, I think, how many free variables are there in this case? 1 for lambda is equal to 1.
Yes, sir. For lambda equals to 1, I'm talking.
Yes.
Yes, sir. I was confused in this. Now I'm clear.
Basically, if you multiply x1 by minus 1, so you get minus 1, 1, and minus 1. And this is also an eigenvector corresponding to lambda is equal to 1.
Yes, sir. I got it.
From this property. And I think the same thing will happen for x3.
Yes, sir. X1 for x3. Yes, sir. This is 1 1 1.
1, 1, 1 is one of the eigenvectors.
Yes, sir. 1 1 1. I'm getting.
Yeah. So from here we notice that the eigenvectors are linearly independent. You can check these vectors that you have obtained, x1, x2. These are all linearly independent. And we also notice that the eigenvalues are distinct. Okay. So now we move to some other properties of eigenvalues stated in this theorem. I'm going to prove only some parts of this theorem. Remaining part are not difficult to prove, so I'll keep this as an exercise for you. So if lambda is eigenvalue of A, then alpha lambda is an eigenvalue of alpha A. This, I put this as homework. Second one is lambda minus K is an eigenvalue of A minus Ki. I put this also as homework. Third one, I'll provide the proof. So third one is 1 minus lambda is an eigenvalue of A inverse, provided lambda is non-zero. So we are given that lambda is eigenvalue of A. So we can assume that X is the eigenvector corresponding to the eigenvalue lambda. This means Ax is equal to lambda x. Okay. Now A is invertible, so we can pre-multiply this equation by A inverse. On the left hand side, you have A inverse Ax. On the right hand side, you have A inverse lambda x. A inverse A will become the identity matrix. So it will be, left hand side will be Ix. Right hand side, you can take this lambda outside. This is just some constant. So you take this outside. So you have lambda, and here you have A inverse x. Then you can take this lambda to the other side. So you can write this as A inverse x is equal to 1 over lambda into x. From this relationship, we get that 1 over lambda is an eigenvalue of A inverse. Okay. So if lambda is an eigenvalue of A, then 1 minus lambda will be the eigenvalue of A inverse, if A inverse exists. Fine. Now the next property. If lambda is an eigenvalue of A, then lambda raised to m is an eigenvalue of A raised to m, where m is some positive integer. Okay, so this also we can prove easily. Since lambda is an eigenvalue of A, so we can again say that corresponding to the eigenvalue lambda, the eigenvector is x. This means Ax is equal to lambda x, just like the previous proof. And then we can start with A raised to mx. A raised to mx can be written as A raised to m minus 1 times Ax. Okay. Now this Ax, we use this relationship here to substitute the value of Ax, which is lambda x. So we get lambda x here. Now this lambda is a constant, so it will come out, and we can write this as lambda times A raised to m minus 1x. And then we repeat this process again. So this can be written as lambda into A raised to m minus 2 into Ax. And then again you use this relationship, Ax is equal to lambda x. So you get this. And again this lambda will come out. So you are left with lambda squared, A raised to m minus 2x. And then you keep repeating this process until at the end you get Ax here. So when you have Ax, the power of lambda will become m minus 1. And then again you use Ax is equal to lambda x to get lambda raised to m into x. So that means we have proved A raised to mx is equal to lambda raised to mx. From there, we can conclude that lambda raised to m is an eigenvalue of A raised to m. Okay, so this completes the proof of this part. Fine. Now, let us see the last part. Lambda is an eigenvalue of A transpose. So we start with the characteristic equation. A minus lambda x, determinant of A minus lambda, determinant of A minus lambda I is equal to 0. Now the determinant of A and A transpose is same. That means we can write the left hand side as the determinant of A minus lambda I transpose, which can be written as A transpose minus lambda I transpose, and I transpose is just I. So this is basically equal to the determinant of A transpose minus lambda I, right? And this is the characteristic equation corresponding to the system A transpose X is equal to lambda. So from here, we can say that lambda is an eigenvalue of A transpose. Is this fine? So this completes the proof of the last part. Any question here? So basically, you see that in some proofs you have to apply this method. To start with this equation and then pre-multiply, post-multiply, really depends on what you want to prove. So sometimes this method will work easily. Sometimes the characteristic equation method will work easily. So when you write down the proof of these first two parts, you think in this direction. Either try to use this one or this one, whichever works, you can use that. If both works, then also that is fine. Any question here? No question?
No, sir.
Okay.
No.
So now it is already 11 o'clock. So how far we can stress today?
Sir, I think this is it, sir. I need
This is
to
it.
go to. Sir, I need to go to eat some.
Okay, no problem, no problem. So we will
Thank you.
stop here and we'll continue the discussion on this eigenvalue, eigenvectors in the next class. I hope I will finish this and I'll start something else also in the next class. So,
Sir,
Thank you, sir.
yes.
can lambda take imaginary values, sir?
Yes, it can.
In which case there won't
But
exist
I think
eigenvectors, or
I think we will not see this situation.
sir, because like in the matrix 0 1 minus 1 0, lambda will be equal to I. So what would that mean, sir?
This is geometrically it is difficult to interpret because when you have this complex numbers, then the complex number lie in a complex plane. So complex plane is entirely different thing. So mathematically you can expect this, but from practical point of view, I'm not sure how much useful is this. But mathematically
Okay,
you can
sir.
definitely expect this.
Okay, sir.
Any more question?
No, sir.
No, sir. Have a great time, sir.
Yeah, you too. Enjoy your
Thank you.
Sunday. Bye bye.
Thank you, sir.
Bye, sir. Thank you, sir.
Thank you, sir.